These are notes section 6.1, angle measures and polygons. Well, let's talk about what a polygon is, right? So it's a closed figure formed by coplanar segments. You've seen these before. This would be a polygon, one example. You could have our regular polygons, we know triangle, square. We have a pentagon. You could draw a pentagon. That's a polygon. A non-example, though, for a polygon would be something that would have a curve, a gap, or an intersection. So this would be one example. If it has a curve, this would be like a semicircle, right? This is a non-example. You could have an open figure. That means there's a huge gap there. That'd be a gap. And then if we have an intersection shape, so let's say we have two lines that cross and one connects. So this is definitely a non-example because there's a huge gap where the figure doesn't even close and it crosses over and intersects. So that is several non-examples. Okay, so how to tell if it's a polygon? If it doesn't have any curves, gaps, or any intersections, it's a polygon. Okay, regular polygons are going to be polygons that have equal angular and equilateral sides. Okay, so it's really important to know what a regular polygon is. So the word regular implies that our polygons are all going to have the same sides that are the same length. So for example, this pentagon here, I can mark it by showing that all sides are the same length. That means it would be equilateral. And regular polygons are equiangular. So if they're equiangular, that means all my angles are the same. So in this pentagon, I'm going to mark that all the angles are congruent. Okay. All right, same thing for this side. Let's make sure we have all the sides the same. And we can tell what shape it is by counting the sides. So we have 1, 2, 3, 4, 6, 7, 8. So it's an octagon, right? So 8 sides makes it an octagon. All the sides are congruent. All the angles are congruent. So this is a regular octagon. And of course here we have a square. And so this would be a regular polygon. Now, if you are given in a problem that it's a regular polygon, you need to know it's the sides and angles that are all congruent. Okay. We also have polygons that are concave versus convex. A concave polygon will cave in at some point. And how do we test that? Well, some shapes are kind of hard to test or figure out just by looking at them. So we can test by drawing a straight line through our shape. So if I draw a straight line, and it comes inside of one polygon, out and in, out and in, that means it's concave. All right, so we'll just write a note here, can test with a straight line, excuse me, if the line, I'll move this over just so you can see what I'm writing. If the line comes out of polygon and back in the same polygon. It is concave. Okay. So if I were to draw a straight line through these convex polygons, it only goes, the line can only go one way, right? It doesn't intersect more than once. And then same with this line. No matter how I draw that line, it's only going in and out at one time. Where here, it's going in and out of my polygon. So that's how we can tell just by drawing a straight line. Okay, so that's one test. Also, concave always makes me think of it caving in. So it caves in here, caves in here. This definitely caves in at some point. So I can know just by looking at it whether it's concave or convex. Okay, so know your straight line test and know just by visual. Okay, now zoom back in here. We're going to focus on some diagonals of our polygons. So I want you to draw on your notes a triangle, quadrilateral, pentagon, hexagon, heptagon, and octagon. So on each one of these, they don't have to be the same size or same length, so they don't have to be regular polygons. They just have to be this shape. All right, so we'll first draw each polygon, then draw the diagonals that you can in a polygon. So a diagonal in a polygon has to have two vertices. So it connects from one vertice to any two non-consecutive. So that means, like, if I look at my triangle here, if I start with this vertex, the next one is here, but that's consecutive. The next one here is consecutive. So my triangle actually doesn't have any diagonals. So a triangle will have no diagonals. So our step 3 here to find the sum is rather easy, because I know by our triangle here that we have 180 degrees. Okay, so one triangle, we know it has 180 degrees. That's the sum of my interior angle measure. All right, so triangles, let's write down how many sides. We know we have 3 sides in a triangle. Now it's important to note the number of sides, and you'll see here in a minute, because it's going to help us figure out a pattern here. Next, let's look at the quadrilateral. It has 4 sides. And if I draw a diagonal, I can actually only draw one diagonal on this quadrilateral. But that creates 2 triangles. So if you can see here, I have one triangle here and another one at the bottom part here. So that gives me 2 triangles. And I take 180, multiply that by 2. And the reason why I'm multiplying that by 2 is because, all right, I know a triangle has 180 degrees, right? So if I have 2 of them, that makes it really easy to find the interior angle measures, right? So 180 times 2 gives me 360. All right, so let's do the same thing for our pentagon. Okay, so the pentagon has 5 sides, and let's start at this vertex, and I have 2 diagonals, which gives me 3 triangles. So if I take 180 times 3, I get 540 degrees. Okay, so each one of these is the sum of my interior angle measures. Okay, so each one boxed is the sum. All right, let's try the hexagon. So I'm going to start my vertex here. Really, you can start your vertex at any point. Now this one, I have 3 diagonals, but I have 4 triangles. And that gives me 180 times 4, which is 720. So 720 degrees. Right? By now you should be catching on to the pattern. All right, so if I use this as my diagonal, or my vertex to make my diagonals. All right, this one I have a heptagon, so a heptagon gives me 4 diagonals and 5 triangles. So that means I'll take 180 times 5, and I get 900 degrees for the sum of my interior angles. The last one, we have an octagon. So we have 8 sides, and I can draw 5 diagonals, which gives me 6 triangles. So if I take 180 times 6, I get 1,800, or 80 degrees, not 800, 80 degrees. Okay. Now what's consistent between all of these polygons has something to do with their sides and the number of triangles. Okay, so 3 sides, 1 triangle, 4 sides, 2 triangles, 5 sides, 3 triangles, 6 sides, 4 triangles, 7 sides, 5 triangles, 8 sides, 6 triangles. So the consistency here is that if I have 8 sides, I have 6 triangles, so that's a difference of 2. 7 sides, 5 triangles, another difference of 2. 6 sides, 4 triangles, difference of 2. Keep going, we have a difference of 2. 5 sides, 3 triangles, a difference of 2. So here's how we can find the sum of our interior angles for any polygon. So if you have a 22-sided polygon, you can still find it without having to draw every single diagonal. What you want to do is you'll take the number of sides, we'll zoom back in here, and subtract 2, right? We had a difference of 2. Then multiply by 180 degrees. So this is by the number of triangles, right? So number of triangles we can find by taking the number of sides, subtract 2, and multiply by 180. Okay. So let's put this in a formula. This formula is actually called the polygon interior angles sum theorem. Okay, so I want you to start this because we will be working on proofs this unit. So the sum of the interior angle measures of an n-sided convex polygon is n minus 2 parentheses 180 degrees times 180 degrees. Right? Where n is the number of sides. Okay, that's why in the theorem it says n-sided. N is the number of sides. Okay. Another thing I want you to highlight or star is you will need to know how to name polygons up to 12 sides. So a 9-sided polygon is called a nonagon. A 10-sided polygon is called a decagon. 11-sided polygon, there's actually several names. You'll see it as 11gon. You will see it as an undecagon, un for one, undecagon. And you will also see it as a hendecagon. A 12-sided polygon is called a dodecagon. Do for two, decagon. So, for example, if you think about it, a 10-sided polygon is called a decagon. 12-sided dodecagon, meaning it's a decagon plus 2 sides. Okay, now let's take a look at the back of your notes. We have another theorem that's called the polygon exterior angles sum theorem. Okay, so this one states it's the sum of exterior angle measures of a polygon, a convex polygon, meaning one angle at each vertex, okay, is 360 degrees. Okay, so what the heck does this look like? Okay, so remember when we would find the measure of exterior angles in a triangle. So I want you to draw a triangle. And let's draw an exterior angle, right? If this is, I'm going to zoom in here. If this triangle, if this measurement is, let's say, 80 degrees, then this exterior angle would be 100. Okay. What this polygon exterior angle sum theorem says, well, all of my exterior angles, so let's draw the rest of my exterior angles of the triangle. So let's look at this angle. If I draw this exterior angle, and if I look at this angle, and I draw this exterior angle, all of them have to add up to 360, and it doesn't matter what type of polygon. If I have a triangle, if I have a quadrilateral, an octagon, a decagon, they will all add up to 360. And that's the cool thing about this sum theorem, is that it doesn't matter which kind of polygon. So let's give some values here. Let's say this this one is 140. Which means this last one would have to be 120 degrees. Okay. Now, 100 plus 140 plus 120, that gives me the 360. Okay. So this theorem is what we will use for example 6. So I want you to star example 6 on your paper, and we'll use the exterior angle sum theorem. Okay. Alrighty, let's try some examples of finding the sum of interior angle measures. So earlier when I was talking about how we can find the measures for a 22gon, well, now let's do that. So the sum of the interior angle measures, 22gon means I have 22 sides. So if I use my formula, the n minus 2 times 180 degrees, let's box this, so this is our formula. 22 would be substituted in for n, because n is our number of sides, so I take 22 minus 2 times 180, which would be 3,600 degrees. Now a heptagon, which we did on the other side, let's prove it by using our formula. So we know that it's 7 minus 2 for n, and multiply that by 180, we get 900 degrees. Now you can check and see if that's what we got on the other side, which it is. Okay. Just remember that n stands for numbers of sides. Move that back over. Okay, let's take a look at our next example, number 3. Now we have the sum of interior angle measures of a convex polygon are given. Okay, so this time we're working backwards. We're still using our formula, the n minus 2 times 180 degrees. But we're going to set that equal to our total that's given. Okay. Then it says to classify the polygon by the number of sides. So once we find that number of sides, then we can classify it. So let's start with this one. 1,980. Set it equal to our formula, n minus 2 times 180. And solve for n. So I'm going to have to divide by 180. And I get 11 is equal to n minus 2. If I add 2 to both sides, I get 13 is equal to n. All right, so 13 sides would mean I have a 13 gon. So that's how we would classify. All right, let's look at number 4. This time I have 2,340 degrees. And I'll set that equal to n minus 2 times 180. And again, we want to solve for n to figure out the number of sides. So when I divide, I get 13 is equal to n minus 2. Add 2 to both sides. And 15 is equal to n. So I have 15 sides. Which means my polygon will be a 15 gon. All right. So our next two examples, if you look at example 5, this is going to be using interior angles. Okay. So when you're looking at your shapes, are two things you want to ask yourself: are you working with an interior angles, or are you working with exterior angles? Right. So this one's interior angles because I'm looking for x. So at some point, I need to find the sum of the interior angles. Okay. All right, so let's just focus on number 5 real quick. Well, let's figure out what kind of polygon we're working with. We have 1, 2, 3, 4, 5. I have a 5 shaded polygon. And so I can know that it's a pentagon. And a pentagon has a sum of interior angles of 540 degrees. So I can take all my angles and I can take 90 plus x. I'm just going to go around this direction. Plus 103, plus 77, and plus 143. And set it equal to 540 degrees. Okay. Then I can combine my like terms and solve for x. So when I add these together, I get 413 plus x is equal to 540. When I subtract from 413, I get x is equal to 127 degrees. Okay. Now let's take a look at number 6. So number 6 starts out with exterior angles. Okay. So this is going to be the sum of exterior angles that I want to use. Sum of exterior angles. All right, so my sum of exterior angles, as you remember, I told you to star this one because then we can use our exterior angle sum theorem. And it doesn't matter what polygon we have, but they will all add to 360. Okay, so I can we'll start at 80. I'll take 80 plus x plus 54 plus 59 plus 2x plus 59 and set it equal to, let me squeeze in that 360 at the end there. Okay. All right, so let's combine our like terms. I have x plus 2x gives me 3x. And then 80 plus 54 plus 59 plus 59 is 252. And that equals 360. Okay. So just solve using algebra. And I get 3x is equal to 108. And divide by 3. My x is equal to 36 degrees. Okay, so I can find the measure of those missing angles. This one would be 36 degrees. And then this one is 36 times 2, so that's 72 degrees. Okay. Okay. All right, our next set of questions. The first one says find the measures of an interior and an exterior angle for each polygon. So the key word here for these first two, 7 and 8, is regular. Okay, so it's a regular 18gon and a regular nonagon. Okay, so because it's regular, remember we talked about this at the very beginning, all the sides are congruent and all the angles are congruent. So 18gon means I have 18 sides. Okay, so let's start by looking at the exterior angle. And I can find the measure of one exterior angle because it is a regular polygon. So an exterior angle means I just want the measure of 1. Okay. Well, remember, we know any polygon has exterior angle sum of 360 degrees. And I know it has 18 sides, so I'm going to divide by 18 to figure out that exterior angle, and that's 20 degrees. So the 20 degrees would be for my exterior angle. Okay. Interior angle will be a little bit different because we know, excuse me, the n minus 2 times 180 is our formula for interior angles. So that means I'm going to have to take n minus 2, n is our 18, so 18 sides minus 2 times 180. And that gives me a value of 2,880. And the next step I have to do to find one an interior angle, so I need one of them, divide by the number of sides I have. So that gives me a 160 degree interior angle. Okay. Now, because it is a regular polygon, my interior and exterior angle must sum up to 180. Okay, so we can always check that these two add to 180, and they do. Okay, which means that they are a linear pair and supplementary. All right. Now let's look at a regular nonagon. So let's start with the exterior, which means I have to take 360 degrees divided by, well, a nonagon is 9 sides, so divide by 9, and that gives me 40 degrees. My interior angle, I'm going to start out the same way by taking 9, the number of sides minus 2 times 180. Gives me the total sum of the interior angles, which is 1,260 degrees. And then I'm going to divide that by the number of sides, which is 9. And I get 140 degrees. Okay. So let's separate this here so we know this isn't part of our equation we're working with. Now, do these sum up to 180? They do. All right, let's take a look at our last two example problems here. So we have the measure of an exterior angle of a regular polygon is 9 degrees. Find the number of sides. It doesn't say what type of polygon it is, but we can figure that out by the number of sides. Okay, so what I want to look at is exterior angle. Remember, we said it's 360. We don't know the number of sides, but I can use the same formula that I did up here. So remember, we took 360 divided by 18 to find our degrees. Well, let's use the same idea. I'm going to take 360 divided by n, the number of sides, what I don't know, and set that equal to 9 degrees. Well, I need to multiply n by both sides, and I get 360 equals 9n, and then divide by 9. N is equal to 40. So that means I have 40 sides. All right, let's look at our last example. This time we have interior angle, right? So that means I'm going to have to use my n minus 2 times 180. And it says that measure is equal to 156. And I'm going to use the same thing I did up here, divide by the number of sides. So divided by n. All right, so if I look here, oops, 180, not 18. We can multiply both sides, or you can look at it as cross multiplying. There's two different ways you can look at it. So I have n times 156 is equal to n minus 2 times 180. Now because I have an n on both sides, and this is in parentheses, I will need to distribute my 180. So I have 156n is equal to 180n minus 360. And then let's solve for n. Okay, so subtract your 180n on both sides. 80n. And I'm going to bring this up here. And I get negative 24n is equal to a negative 360. Continue to solve. Negative 24. Divide negative 24 on both sides. And n is equal to a positive 15. So that means this polygon has 15 sides. Okay, and that's it.